Okay. Hey. Thank you for that nice introduction, Daniel.
Hello.
Yeah, I'm Vivek.
Hi, and I am Christos. And today we're going to talk to you about a project that we've been working on called Golf Course Wayfinding.
Yeah.
So the goal of this project is to identify and categorize the different areas that we have in a golf course. Golf courses is one of the biggest customers for Husqvarna, especially for professional robotic mowers. Through the Green Space Evaluation Initiative, Husqvarna wants to have a better understanding of the operational environment of their products, and they want that because they want to improve the quality of their products and the services that they provide to their customers. So if you're like me and you have never played golf in your life, this is an overview of how a golf course can look like if you look at this image. We have different areas. First and foremost, we have the fairway. The fairway covers a big part of the golf course, and because of that, we have larger models operating there. Also, the grass is a bit lower, meaning that it's mowed more frequently. Surrounding the fairway, we have the rough and the semi-rough. In our case, we consider it as one category, rough, and there the grass is a bit higher. We also have areas like the green that is smaller and more detailed and surrounds the hole. And this is where smaller mowers are operating, or it is handled manually. Same is applied for the tee, which is the starting point of the golfer. Our starting point is that we have data about golf courses and their perimeters across Northern Europe. We also know the mowers that operate in these golf courses, and we have sensor data for these mowers as well. Our first goal is to identify the different fairways in these golf courses, and in a more long term, extend it with the rough data as well. Our initial approach looks a bit like the diagram here. We want to utilize computer vision in order to identify the areas on satellite images of golf courses. In order to do that, we want to build a dataset that consists of images, satellite images, that we can get from the golf course perimeters, and also semantic masks that we can get from our internal data. We want to use our internal data as a semantic mask because we want to preserve the mowing characteristics. Our goal here is to prove that this project is feasible and that our data can support it. A few words about the image generation. As I mentioned, the starting point is the perimeters. So what we can do next is that we can generate a bounding box around its perimeter. Then we can provide this bounding box in a library like OSGeo and utilize standards as GeoTIFF and generate images that have an additional layer that contains geospatial reference for each pixel. We want that in order to match the images with the semantic masks that we have extracted. Finally, we need to split these images into tiles. We have golf courses that have different sizes. But in the end, we want to have standardized images, images with the same number of pixels, dimensions, and resolution. Our main source of data for extracting the semantic masks are spatial points of mower movement. We can use these points in order to generate cells, and then we can match these cells with the pixels of the images. Each cell needs to have a label, indicating if it's a fairway, a rough, or another area. In order to give the labels to these cells, we utilize product and operation metadata. The product metadata are mostly focused on the mowers, for example, what model it is, while the operation are mostly focusing on the mowing process, what mowing cycles we have, what is the charging schedule, and so on. Now, using this data, we had different challenges. First of all, we have high complexity on our annotation rules. Not all of golf courses are mowed the same way. that makes it hard to build one solution that covers everything. Because of that, and the fact that we're using points, we ended up with a lot of outliers that we have to take care of in our data post-processing pipelines. Finally, we want to annotate as many pixels as possible, meaning that we have to collect as many points as possible. So our pipelines have to go through a lot of mowing cycles to cover that, making them execution heavy. Taking these challenges into consideration, we realized that maybe by using this data, it will be too hard to scale. They have been proven successful in previous projects that we've been working on, very helpful, but does it mean that they are the right option, the right choice for this project? This is when we decided as a team to take a step back and start exploring other available options that we might have. We decided to explore the data mesh in order to find more data sources available. We had interviews with specialists in order to understand the domain knowledge behind the mowing process. And then we just annoyed people with questions in order to match the domain knowledge with the data sources that we have found. And this is when we decided to make our first big decision and basically pivot to a different data source that we can extract SVG maps, and it comes from the Husqvarna planning application. So what is so special about the SVG maps? First, we can extract polygons and not points. Each polygon is coming with a label indicating if a mower can operate or not operate there. Moreover, each polygon is coming with a description in natural language describing its purpose. So we can combine these 4 polygons that we have here into 2 very well-defined annotated polygons. We have way less entries to handle since we don't have to mess with pixel by pixel now. We have reduced complexity because we can annotate a lot of pixels. And of course, we have an additional layer for our annotation logic. In our annotation logic, our main purpose is to minimize human intervention. Basically, we don't want to do the annotations ourselves. We use the more metadata, the product and operation that I described before, to create golf course characteristics. And we also use the description of the polygons. The challenges that we need to face is, of course, the planning logic, how each golf course is mowed, as well as the multilingual descriptions, meaning that polygons in golf courses in Sweden most probably will have a description in Swedish. Same in Denmark, and so on. So for our first approach, what we did is that we selected a subset of golf courses that we know how they look like, we know what areas they contain, and we built our annotation logic there, and then we applied it to the rest of it. In the future, we want to introduce some evaluation processes, as well as better adaptation when we introduce new golf courses from different countries. So we're good to go, right? We have everything we need. Well, not really. There is an underlying problem that data processing cannot really solve. And that has to do with the mower coverage. If you look at this picture here, first of all, we don't have any roughs. And that's OK. We knew it from the beginning that the roughs is the long-term goal. It's something that it's not focused as a first iteration of the project. Our data cannot really support it from the beginning, so we decided to explore it in the future. What is more concerning is that we have a lot of fairways that they are not annotated with polygons from the semantic masks. That can be an issue, and it can affect the performance of the model, because if we provide this image with this semantic mask, a lot of pixels will be false negative, meaning that they were labeled as background when actually they're just a fairway. So what should we do? Should we pivot again? Maybe this time we can just take a shortcut. As I mentioned before, our highest priority is to prove that this is a feasible project. We can only focus on the fairways, and now we have reached a point where we have a better understanding of our data, what we can do and what limitations we have. So we decided to shuffle our logic a little bit. instead of training a dataset with our own data, we use an external dataset that contains classes from areas of the golf courses, including fairways, but no roughs. Then we can use that model into an inference pipeline that will take as input the satellite images that we have generated. This inference pipeline can run in parallel with our spatial analytics pipeline that provides the semantic masks. So in the end, we can have two different views of the same golf course that we can combine, and they can fill each other's gaps. So far, I have spoken about the image generation and the spatial analytics part, and now Vivek will dive deeper into the model training and the computer vision.
Yeah. Thank you, Christos, for setting the stage. And I want to learn how to use this pointer. Yes. So, yeah. So in this part of the work, like Christos mentioned, that we now pivoted to some publicly available data set, and our main focus is to really prove the value fast to the stakeholders. And in this part, let's see. Yeah. So in this part, so we built a model training pipeline for computer vision and specifically semantic segmentation. So semantic segmentation basically means that given a pixel, we want to classify that pixel into a fairway, rough, or some such other class that is interesting for us in a golf course, and especially for Husqvarna. And so for this particular pipeline, since we wanted to start many experiments because we don't know which kind of model will be the best one. So we wanted to build a model pipeline thinking about how easy it should be to start many experiments at the same time. And so here, like we built in this model training pipeline, ease of configurability. So we start the experiment with some configuration. We want that to be super easy. One file, you put all the configurations. And then we built the pipeline such that we are able to try many different models without changing much of the infrastructure. And so we built like a very fast model iteration, so we can in place replace the models that we try. And then we also built the ease of observability. So when we are training such a computer vision model, we want to be observing what's happening during the training. And for this, we utilize TensorBoard and CSV Logger. And then at the end of all of this, we want to like obtain a very portable model so that it's not tied down to the same infrastructure where we are training, because usually it's quite a lot of compute. But for the inference part, we don't need, especially in this computer vision model. And then in particular for the models here, what we wanted to try is something that has out-of-the-box like ability to understand basic shapes and environments. And for that, we use some pre-trained computer vision models that have been trained on publicly available data like the ImageNet and COCO dataset. So next. So once, in particular, like I want to highlight here the very usefulness of PyTorch Lightning framework if you're exploring deep learning training. So in this pipeline, we utilize that framework, and that's because we wanted our code base to be very clean, readable. Any new person coming in understands what's happening, and PyTorch Lightning framework really provides that. It has a lot of pre-built hooks for a lot of the training, validation steps, model checkpointing, calculation of metrics. So our code base is really readable and clean, and it really allows us to experiment. And most importantly, I want to highlight the hyperparameters that helped us in getting a really good model at the end. And one such is that that we pre-compute this class weights. So basically, what Christos described, we have this classification problem, but then it is also highly imbalanced. We have one class being in too many, and then other like T areas which are too few. And we want the model to, like, when it computes the loss functions and the metrics, to use those as weights so that it understands that we really have a class imbalance problem. And then another thing that we explore is this learning rate scheduler. So this is basically, in deep learning model training, learning rate is one of the most important hyperparameters. And if you have ever looked at any kind of partial differential equations or ordinary differential equations, you would know what I'm talking about. This is the adaptive technique where you reduce your step size. So this particular helps during the training for the model to explore like a lot of different parameter space. And then we, like I said, that we built ease of observability. So we monitor the loss function itself to train the model. And then to do such training, we also need compute. So we utilize this NVIDIA Tesla T4 compute. And once we have the model, we then port it to this ONNX format. It's highly portable, can be deployed on GPU or CPU infrastructure. And then we built an asynchronous inference pipeline using our trained model. And the difference between having a synchronous and asynchronous is that basically in a asynchronous pipeline, you queue a lot of your tasks, and then they are batched together and provided to the inference worker. In asynchronous, you also queue, but then these are first in, first out. So here, a lot of the time, the inference pipeline is just sitting for the task to be done, whereas in asynchronous, it is doing whichever happens fast goes out the first. So this really reduces our time of this inference. And then once we have a good model, we have the predictions, we want to do some sanity check. And here, what we see is the same satellite image that Christos showed, and this is from our internal polygons. And then we overlay with our predicted fairway from the model that we train. And we can clearly see a lot of the areas. And one thing to highlight is that in our internal IoT data, we don't have green, but from the model training, we can, because we use publicly available data. And then we overlay with our internal IoT data pipeline, and we can see how much is Husqvarna mowers coverage compared to what is the total potential for that golf course. So this is kind of a byproduct of this, the mower coverage that we find. Apart from this predictions and the internal IoT data pipeline becoming the backbone of a spatial analytics pipeline that is then used by other teams to really bring value to their areas. So in conclusion, from my side, during the course of the whole project, my take-home message is that we need to work on proving the value fast rather than making a model very accurate. So once we have proven the value, we can invest a lot more infrastructure and cost in doing all the fancy stuff. And then again, there is always a limited infrastructure, so we always need to balance the value and the cost. And that's from my side. And then now I will leave to Christos for his concluding take-home message.
From my end, what we can add is that on projects like this, domain knowledge is essential, and it takes a lot of time to get it. It's not so easy, especially if you're a data engineer or a data scientist, to understand the full picture, but it can be very helpful when you reach that point. And what was also really helpful for how this project is evolving is that we are two people with different niches, different interests, that the moment that we started collaborating and working together, it speed up the whole process a lot. That's it. Thank you for listening.
Thanks a lot. Yeah.
Christos and Vivek, thank you so much for such a great talk. And I think our audience had also a lot of fun listening to you. we have a very hilarious, the most upvoted question for you. You ready?
Yeah.
I need to, for the sake of democracy, I need to tell you. Why are you not playing the sport yourselves? A man not playing golf is a man you can't trust. You don't have to answer. You don't have to answer.
Point taken.
Okay. Thank you to the humor, the afternoon humor of the audience. So now more seriously, tell us more about input data collection, curation, and annotation. How often is it updated, and how much does it change with any updates?
Yeah, I can take that. So the data for the golf courses that describe the golf courses, like the perimeter and the satellite images, are mostly static. The golf courses do not change so much during the year. So when we introduce new data, our partition, in a way, our asset is basically the golf course. If we have that, then we're good to go. Now, regarding the polygons, what happens is that depending on the season and depending on how things have changed, different mowers might operate there. So the whole landscape of polygons that we see from the mower movement might have changed. And we choose to update this data on a monthly basis that goes together with the other projects that provide us the information of the mowers, for example, that operate there. So they are all refreshed at the same time.
Thank you very much.
And most of the changes are shown in summer or in spring because that's when people play golf. That's what they told me.
As new data comes in.
And that's when the data comes in.
What are the major limitations of your model annotation and training pipeline?
Yeah, that's something I can take. So I didn't
So you
mention...
take the bad stuff, it takes the good stuff. Okay, got it.
Yes. Yeah, the model limitations, of course, like this is kind of the, so to say, the first iteration of end-to-end value creation. So what we want to invest more time is improving, like I said, that what as a byproduct we got is a mobile coverage, but it also is that we see how good our internal data is. And so our model and the IoT data go hand in hand to enrich each other, so to say. And yeah, we have a lot of ideas to improve this model, the IoT data pipeline. So we will explore.
Thank you so much. Yeah. So another question from the audience. Did you explore using foundation models like MetaSAM in your workflow? And how did they compare to your chosen approach?
We explored that option when we started with the project. We haven't really compared them as of now. The limitations that we have with objects like this is that they needed a point in order to operate. There are some cases, as you saw in the case that we do not cover all the fairways, that we cannot provide that point programmatically.
Yeah.
And that was the reason that we decided to train our own computer vision model.
Yeah. And I think it also relates to this point that I was saying about proving the value fast. So our focus has been really to show the stakeholders that this is the value that they can get out of this if we invest more. And as they start using this, then we have more infrastructure and investment to improve on this. So I would say that it's model comparison and improving the model is like the next step of proving the value.
Well, thank you so much for your talk and for answering all the questions of a very curious audience. And please join me in a round of applause for Christos and Vivek.
Thank you.
Thank you.
And please accept a gift from our cat.
Thanks.